Hello everyone, welcome to my PhD defense. As most of you know me, my name is Golshid, and I'm a PhD candidate in the framework of a European project called Pioneer, in a co-tutel agreement between Sorbonne University in Paris and Institut Supérieur Technical in Lisbon under supervision of Dr. Da Costa and Dr. Henriquez. And today I'm going to talk about the effect of promoters in a nickel-based catalyst for two different supports in a DVD plasma. Today, shortly, I'm going to say like a small introduction, why we are doing this work, why CO2 hydrogenation to methane, why catalysis, why plasma, and then I will show you the experimental setup of this work and how it works to have the results. Then I'm going to show you the results and discuss about all the results that we received. Then I'm going to point out some conclusions and give some perspectives for the future work. So, from a long time ago, since now, with the progressing of the civilization, the demand for energy increased. Since 60 years ago up till now, more than 80% of the energy sources are coal, oil, and gas. And these are actually the fossil fuels. By using these source of energies, the harmful gases, the harmful chemicals started to pop up, such as NOx and greenhouse gases. Greenhouse gases, which on top of them is CO2. The accumulation of CO2 in the atmosphere started to pop up all around the world. As a result of trapping the greenhouse in the atmosphere, the temperature started to increase all around the world, and environmental crises started to pop up, such as flood, heat waves, increasing of the sea level, and like this, climate change and global warming started to appear, and cities and land started to change. Here, as you can see, there is two different pictures. No matter where do you live, you're still infected by this crisis. First picture is in Paris in 2014 by few months difference. While the second picture is my city, Isfahan, which it was taken by 8 years difference when yes.
But we don't see the presentation. We are stopping the first slide.
Okay, because it looks that it's shared here.
We don't see it online. We just saw tailoring selectivity with different plasma sources and your name, the first slide. And also I would like to say that the people following the presentation, maybe they should stop the microphone, please.
Yeah, that's true. Yes. Yeah, that's the show. Okay.
Now we see another slide with two Earths.
Yeah, wait, I'm trying to reshare.
Okay. And could you please then mute everyone?
Yes.
Because, yes. Microphone? Okay. Okay. Sorry, I didn't know.
think you already spoke about it, no?
Yes. I already spoke about this part. So basically, I was here. Yes. So I was here.
Maybe go ahead with the previous one, please.
Yes. Okay. Oh yeah, sure. Yes. Okay. So yes, as I was explaining, as a consequence of trapping greenhouse gases in the atmosphere, the temperature started to increase all around the world, and the environmental crisis started to pop up, such as drought, flood, heat waves, and increasing of the sea levels. And like this, climate change and global warming started to appear, and cities and land changed. No matter where do you live in this world, you're still affected by this. As you can see, first picture is in Paris in 2014 by a few months difference, while the second picture is my city in Iran by 8 years difference when the river was completely dried because of the global warming. As a consequence of similar matters all around the world, in 1997 in Kyoto and then later in 2015 near Paris, 195 nations from all around the world gathered for the first time in a single agreement to discuss about cutting the greenhouse gas emissions, which 194 of them agreed to sign the agreement. The idea was to reduce the CO2 emissions by some methods in order to be able to fight against global warming. So they, by that mean, they agreed to build a closed carbon cycle in order to have a net zero emission by 2050. Talking about the closed carbon cycle, carbon can be captured from exhaust gases and atmosphere that can go through the separation process in order to have the concentrated CO2. Then this CO2 can be react with hydrogen and electricity from renewable energy in order to produce synthetic natural fuel gases or organic materials. The production of these materials will produce CO2, which can be absorbed by plants or directly injected into the CO2 emitting facilities, and this cycle will continue again. And like this, in order to summarize, carbon can be captured and utilized in order to produce good chemicals. And like this, we have a closed carbon cycle and hopefully net zero emission. As it was explained before, one of the processes in CO2 utilization is the reaction of CO2 with hydrogen, which comes from the water electrolysis, and the electricity comes from renewable energy in order to produce synthetic natural fuels such as methanol, dimethyl ether, but more importantly, methane. Methane is a transportable fuel. But more importantly is the feed to the Fischer-Tropsch reaction, which can produce syngas. All these features make methane an important fuel in the energy industry. However, in order to have the highest outcome of a product, it's important to know the kinetics and thermodynamic of a reaction. Methane can be produced from by the reaction of CO2 hydrogenation or Sabatier reaction. Sabatier reaction is thermodynamically favorable, but it has some disadvantages. As it can be seen, it's an exothermic reaction. So on one hand, at low temperature, the kinetics are not favorable. But on the other hand, at high temperature, the CO2 conversion decreases. Also, it's slow, and without a catalyst, you cannot really expect a high yield. Regarding the pressure, with increasing the pressure, the reaction tend to produce more products, but by increasing the pressure, there would be the possibility of parallel reaction and formation of byproducts, which are not favorable. All these matters and conditions make methanation not favorable from the economic point of view in industry. So we already talked about the CO2 methanation and kinetics and thermodynamics. However, it's important to know CO2 itself. CO2 is a highly stable, non-reactive gas, which needs some material in order to activate it. Based on the literature, a highly active metal-based catalyst can activate CO2. Based on several studies, nickel-based catalysts are the best catalysts for CO2 methanation, as nickel is highly active, but more importantly, it's really cheap. However, nickel is in the need of a support to be sufficiently reacted during the reaction. The most important properties of proper support is high surface area, proper acid-basic properties, and adequate interaction of metal support. Last but not least, a promoter in order to improve the physicochemical properties of the catalyst, which can improve the redox and basic properties of the catalyst. Based on the literature, rare earth metals and transition metals are the best promoters for CO2 for nickel-based catalyst. So as we already discussed, CO2 methanation is thermodynamically favorable, but there are some barriers. In order to show you these barriers, I gathered some data from some nickel-based catalysts in CO2 methanation. All the reactions were done at atmospheric pressure and between 200 to 450 degrees. As it can be seen, the best catalytic performance was for nickel seria. However, for all the catalysts below 300 degrees, there was no activation. Also, the fact that at industry it should be done at high pressure in order to avoid catalyst deactivation and CO formation brings some obstacle which needs to be overcome by some methods. So as we saw the barriers, we could say that CO2 methanation shall be done at atmospheric pressure and low temperature in order to have a high conversion. By some method, the needed energy should be reduced in order to have high conversion and avoid catalyst deactivation by time as catalysts start to sintering at high temperature. By this means, the plasma can provide all these conditions for us in order to be able to have good catalytic performance. However, what is plasma? Plasma, as the fourth state of matter, plasma is a partial or totally ionized gas, including excited neutral and charged species, which are electrically neutral. Plasma can be produced between a high voltage electrode and a ground one by applying an electric field. While the excitation happens near the high voltage electrode, the ionization takes place near the ground electrode, and by this means, plasma is produced. In general, plasma can be divided into two types of non-thermal and thermal plasma, which in this work we are going to use the DVD plasma non-thermal, which is thermally non-equilibrium and can be operated at atmospheric pressure and low temperature. And by this, plasma can be a solution to overcome the kinetics and thermodynamic barriers. However, it should be said that plasma catalysis in a complex process. In the heart of this process, there is a catalyst which is containing of active phase promoters and support, which each of them can be from different materials based on their application. As a body of the system, there is plasma, which has also different parts. By varying the reaction condition, the catalytic performance can be changed, while by varying the reactor configuration, the system can be optimized. And finally, using different plasma configuration can change the catalytic performance. All of this together, plasma and catalysis can affect each other, which is called synergistic effects, meaning that the combination of these two, plasma and catalyst, can have more beneficial effect comparing to use each one of them alone. So now we saw the context of the study. It's time to take a look at the experimental part. Here is the scheme of the thermal setup. All the thermal process were done at the same condition and at this setup in order to have the results. But how this thermal reaction was operated? So first, the nickel-based catalyst was thermally reduced in situ in a 5% hydrogen argon flow at 500 degrees for 1 hour. Then it was cooled down below 200 degrees. Then with the mentioned condition, the reaction started. At each step, the catalyst was kept for half an hour, and then the temperature increased with a ramp of 10 degrees per minute. The idea was to see the effect of promoters in this condition, to choose the best promoter for plasma application. Here is the scheme of the DBD plasma setup. Again, all the experiments were done at this setup, and this setup was built from the scratch in Saint-Cyr campus. Regarding the operation of the, yes, I just wanted to show you the real setup. As you can see, this is the ground electrode, while that's the quartz part. The internal part is the high voltage electrode, and yes, here we have the water trap. But how this plasma DBD operate? Similar to the thermal reaction, the catalyst is thermally reduced and moved to the plasma reactor. Then it will be flushed by pure hydrogen and plasma for 10 minutes in order to clean the surface. Then the performance will be done at 3 different voltages. At each voltage, the condition will be kept for half an hour in order to make sure that the condition is stable. And then each 10 minutes, the different measurements will be taken in order to analyze the result. I should also mention that the condition of the reactor was adiabatic, and there was no use of external heating. And also the power measurements were done by Lissajous method. Regarding the catalyst synthesis, it was said that a nickel Syria-based catalyst was used in this study. Syria was chosen because of its remarkable features, such as good oxygen capacity and mobility and high basicity properties. So the catalyst was synthesized by wet impregnation method. All the materials were mixed together as stir at 65 degrees for 4 hours. The impregnated sample when then dried in an oven over the night at 100 degrees. The received sample was calcined with air at 500 degrees for 4 hours, and then the received catalyst was promoted with the mentioned promoters in order to choose the best one, and then later impregnated in a zeolite. Obviously, several characterizations were done in order to understand the physicochemical properties of the catalyst and to be able to predict their behavior in catalytic performance. So let's discuss about the results and see what we discovered based on this study. To give you a general idea of the cases of studies of this work. So the idea was to study the effect of promoters in a nickel-based catalyst, then to see if the promoters can affect the physicochemical properties of the catalyst, the type of promoters and also their loading, either in thermal or plasma, and then use those information in order to impregnate the proper catalyst in a zeolite base and perform the catalytic performance in thermal and plasma. In the first study, as I mentioned, the nickel Syria catalyst will be performed in plasma and thermal. But just to give you a simple comparison between plasma process and thermal, as it can be seen, in plasma process, the CO2 conversion reached to 72% at 160 degrees. I should mention that this temperature is the reactor temperature. While in the thermal process, there is no conversion below 160 degrees, basically until 300 degrees. Then by increasing the temperature, conversion reached to 78%. Yes. Regarding the physicochemical characterization of the catalyst, for this series of the catalyst, the addition of nickel in general increased hydrogen consumption while it decreased the BT surface area. By the addition of promoter, different trends were seen in both BT surface area and hydrogen consumption based on the type of promoter. Regarding the TPD profile of this catalyst, as it was already studied, medium basic sites are responsible for better performance in CO2 methanation. Here we can see that copper, lanthanum, praseodymium has higher medium basic sites. which could be expected that they would have better catalytic performance. However, copper is the catalyst for metal production, so it will be expected that lanthanum and praseodymium promoted samples will have better performance. Also, regarding the nickel particle size, with the addition of promoters, different nickel particle size can be seen. These different particle size are due to the different interaction of active phase and support. There we are. Here is the thermal methanation reaction of 5% loading of the promoter. As it can be seen, more or less all the samples have the same CO2 conversion except for copper and iron. However, the behavior of copper was already justified. So with this type of promoter and this loading, there is no significant increase in the case of CO2 conversion. Also, it should be mentioned that the catalyst after the reaction showed smaller samples, showing that they are more resistive with the addition of promoters to sintering. Also, in order to study the stability of the catalyst, the stability test was held under thermal condition at 250 degrees for 5 hours with the same condition as methanation. As you can see, in the first 20 minutes, the CO2 conversion slightly decreased, but till the end of the test, the conversion and selectivity remained the same, showing that the catalyst was stable under thermal condition. Moving to the plasma test, just to show the importance of catalyst presence in the plasma, I showed different tests under plasma condition. As it can be seen, without catalyst and just with the support, there is no significant activity, while with the addition of the catalyst, the CO2 conversion increased by more than 50% and reached to 72%, while the temperature, which is the temperature of the reactor, remained the same. Regarding catalytic performance of the promoted samples, so it was said that the non-promoted sample has 71% CO2 conversion, while praseodymium, lanthanum, and yttrium has a slightly higher CO2 conversion, while the best catalytic performance for praseodymium promoted sample. But as you can see, there is no really high activity regarding the addition of a promoter. So it will bring the question in mind if they do not increase really the activity. So what is the effect of promoters? When we are talking about plasma, one of the most important aspect of it is power consumption. Even though if we have the best catalyst, if it consumes lots of energy, then there is no advantage of using plasma over thermal condition. As it can be seen, with the addition of promoters, there are different range of power consumption in this series of the catalysts. Even though praseodymium showed the highest conversion, but it can be said that yttrium has the best catalytic performance, as it has slightly lower conversion, but much lower power consumption, which is really important under plasma condition. One specific thing can be said about this is that the yttrium has the smallest particle size in this series. Just to also show that the size of particle size after plasma were smaller under plasma conditions, showing that this series of the promoters were more resistive to sintering under plasma than thermal. But also there is one more interesting point, is that some of the particle size remained the same, or they started to be bigger, which is due to the fact that there is low temperature under plasma condition and more oxygen availability, which makes the reoxidation of nickel and the production of nickel oxide again. And by this fact, the size can be bigger, or it can be the indication of hotspot. Yes, thank you. So I gathered the whole physical-chemical properties of the different properties of this series of the catalysts in order to see if is there a specific trend in, if is there a specific trend regarding properties of the catalyst. It can be seen that there is no specific trend for different properties of the catalyst, which means that there is actually another property which play an important role under plasma condition, which can be either physical property or an electrical. So moving to the second part, we already saw that these promoters with this amount of loading did not really affect the catalytic performance. Based on the literature studies, if you decrease the amount of loading, the catalytic will improve significantly. So let's take a look if this really can happen under either thermal or plasma condition. I did the same characterization on this series of the catalysts. Just to summarize everything, I gather all the information in one slide. As you can see, by decreasing the amount of promoter, the medium basic size increased significantly, which can be already expected from this series of the promoter to improve the catalytic performance. Regarding the hydrogen consumption and also the BET surface area, it can be also seen that based on the type of promoter, different trends were seen. Also regarding the particle size, more or less all the samples have the same particle size. However, lanthanum has the smallest and praseodymium promoted sample has the biggest particle size. Regarding the thermal methanation, cobalt promoted sample showed the best catalytic performance as it has the highest amount of basic sites and hydrogen consumption. Well, while regarding the catalytic performance under plasma condition, it can be seen that interestingly, this series of promoter with lower loading of promoter, they all have higher CO2 conversion under plasma condition. However, the best catalytic performance goes for the lanthanum promoted sample with 80% CO2 conversion. It would be interesting to see if also this catalyst has the best catalytic performance regarding power consumption or not. As it can be seen, interestingly, also lanthanum has the best catalytic performance also regarding the power consumption. Also under this condition under plasma, this series of promoters showed more resisting to sintering than under plasma, under thermal. Sorry. So just to summarize, we already saw that the 1LA promoted sample has the 80% conversion and 35 watt power consumption. Also, it has the smallest particle size, and comparing to the previous catalytic performance, it showed even better performance with lower loading. Again, I gathered the different properties of the catalyst. Again, it can be seen that except the small particle size, there is no specific trend. So definitely there is another property that play an important role that we'll see later. Last but not least, post-mortem analysis such as TGA in order to see if there is a possibility of cock deposition on the catalyst. As it can be seen below 400 degrees, there is a mass loss which is correspond to the loss of water, while at the high temperature there is the mass loss is negligible. The negligibility show that there is no CO2, there is no cock deposition at this catalyst. So to conclude these two part of the study, under plasma condition there is a lower temperature, so there is a lower energy activation needed, while under thermal there is higher temperature and higher need of energy. While we saw that there is a reoxidation process under plasma catalysis which keep the catalyst activated. Why the high temperature under thermal condition brings the possibility of the activation of catalyst and carbon deposition. Also, different type of promoters such as yttrium and lanthanum with different amount of loading improve the catalytic performance. But in general, it should be said that physical-chemical properties should be controlled based on the type and amount in order to be able to have the highest efficiency in plasma CO2 methanation. So regarding the last study, we already explained that the idea is to see what is the best catalyst in the previous studies in order to use them as the active phase in the zeolite-based catalyst to see if they can have sufficient performance in thermal or plasma. So the effect of promoters in the nickel-ceria catalyst was studied in the previous section in thermal and plasma. Even though nickel-ceria showed promising result in CO2 methanation, however, the cost of the economical aspect of the catalyst is still a challenge due to the high cost of ceria. Also, with the addition of 1% of rare earth metal, we already saw that the catalytic performance improved. These series of materials, which are also known as critical raw materials, they are the essential commodities for EU economy, and also they are the key points of Europe's environmental and defense ambitions. However, the high cost and limited availability of them need an alternative path in order to overcome this obstacle. One alternative path is to use zeolite-based material. In this study, we decided to use the HUSY zeolite because of its tunable studies, such as metal support interaction, good dispersion, and also the fact that it's commercially available and it's more economical compared to ceria. So let's have a look at the physicochemical properties and then their catalytic reaction to see how they react. Before moving to the physicochemical properties, I decided to also study the metal incorporation order to see if it has any effect for physicochemical properties. So in the first method, all the materials were mixed together and they were synthesized in the same condition by wet impregnation method, similar to this previous study. While in the second method, first nickel was impregnated, and it went to the all steps of wet impregnation. The received sample was then impregnated by ceria. All the process were repeated again, and the second sample. Yes, the second sample was received, which I named them as TOG, means they mixed together, while the second sample was named as SEP, means they were mixed separately. Based on their physicochemical properties, in general, addition of ceria improved the physicochemical properties of the catalyst, while for the separated samples, the nickel particle size increase, which shows the effect of agglomeration, and also the fact that with the addition of ceria, the external surface area decreased, showing that with the addition of second metal oxide, as they block the entries of the pores of the zeolites, the external surface area decreased. Also, regarding the TEM and mapping shows that the TOG sample has smaller particle size, and also the particles are more dispersed on the support compared to the separated one. Regarding the thermal methanation, obviously can be seen that the TOG sample has the best catalytic performance, not only about the conversion, but also about the selectivity, with 78% CO2 conversion. Also under plasma, not only addition of ceria promoted the catalytic performance, but also the TOG sample has the best catalytic performance among them. So it has been decided to use the previous promoters in order to continue the study of thermal and plasma CO2 methanation. So the previous best catalyst of the study added to this zeolite-based catalyst, it can be seen that the cobalt and yttrium has the smallest nickel size, which it is expected based on the previous study that they would show the best catalytic performance. Also, cobalt-based catalyst has the medium basic size, which are also essential properties. Regarding the hydrogen consumption and external surface area, they are more or less the same, with some differences based on the type of promoter. So simply regarding the thermal methanation, cobalt promoted sample has the best catalytic performance compared to the others, while the others have slightly lower CO2 conversion. regarding the plasma performance, again, it can be seen that the addition of promoters really improve the catalytic performance. Also the selectivity, obviously. Also, cobalt showed the smallest particle size after plasma, and in general, mostly they have different particle size after plasma test. While regarding the power consumption for zeolite-based catalysts, it can be seen in general for zeolite-based catalysts, the power consumption is higher. While it can be said that probably the yttrium promoted sample has the best catalytic performance, however, the selectivity is slightly low. But as the carbon cycle is closed, it can be say that the only byproduct is CO. The important properties that they were playing an important role here were a small particle size and a high amount of basic sites. So to conclude this part, we already saw that with the addition of Syria in general to the catalyst, the catalytic performance improved. The order of metal impregnation actually play an important role in the physicochemical properties of the catalyst, while the co-impregnated sample had the best catalytic performance. A smaller particle size and higher amount of basic sites are the important features for the activity in plasma condition. Just to have a comparison with the previous studies, I gathered the data of the previous studies of nickel based on metal oxide catalysts for DBD plasma in CO2 methanation. It can be seen that the result of this work is almost in the same range, while we have much higher GHSV. While regarding the zeolite-based catalysts, the result of this study is slightly lower, which probably is also due to the very high GHSV. So to conclude and see perspectives, first I'm going to give you a small conclusion. Okay. We already studied the effect of promoters in nickel Syria catalyst. We see that with the addition of promoters, the catalytic performance can improve based on their type. With the first series of 5% loading promoter, yttrium has the best catalytic performance. But not only the type of promoter, but also the loading play an important role. While in the second group, the 1La promoted sample showed the best catalytic performance. And in the last study of zeolite-based catalysts, in general, the addition of Syria significantly improved the catalytic performance, but also the order of impregnation for synthesis of the catalyst plays an important role, while particle size, basic size, also important features for activity under plasma condition. Just to have some perspectives regarding the future works, it would be interesting to perform some long-term stability under plasma condition, as the presence of hotspot can induce the catalyst stability. Also, the reaction can be done in different operation conditions in order to optimum the system. Also, having different spectroscopy and FTIR study would be interesting to study the reaction mechanism of methanation in the presence of this specific kind of catalyst. As I already mentioned, that there is another property which actually play an important role, and there was no specific trend to justify the catalytic behavior. Dielectric constant could be a very important aspect in the plasma condition. Also, the study of impact of impurities of inlet gases, because mostly in industry, CO2 comes from the biodigesters, which always have impurities, which can affect the catalyst activity. Also, influence of packing materials such as bit size, which can affect the plasma properties for sure. And also using different plasma sources for this group of the catalysts, and measurement of water affinity for measuring the basicity of the catalyst. Thank you for your attention.
Show us the